Now that we have an idea of what you're looking for, let's try some functions. As we saw before, any polynomial function we choose will not satisfy the boundary condition of having values between 0 and 1. Of course, we can always cut the curve and limit the x's to values that result in y's between 0 and 1. But we really want is a function covering all the values for x. Now, let's try another family of equations, say square root of x. What we have succeeded in doing is limiting y values to non-negative values, but they can still be higher than 1. And on top of that, the domain is now limited to positive x's. We can try to fix this, say, by using the absolute value of x instead of x. As you can see, the problem of domain is solved, but still not bound by these two lines. So how about using the reciprocal of that equation? Now you have the added problem of asymptote at x equals 1. Well, let's fix that. If you add 1 to the denominator of that equation, you have fixed the problem of asymptote. And the domain covers all the values of x, but the problem is that it's not S-shaped and it's not smooth. So this looks like a dead end as well. What if we try exponentials instead of powers? So here you can see the problem. The domain covers everything, but it's not bound. What if we divide it by x squared? Still, you can see an asymptote here at x equals 0. How about you add 1 to the denominator? Now, this looks much better, and there is no asymptote. And it is kind of bound for some part of the some section of x's. But then again, as x approaches infinity, y approaches infinity as well. That is because exponents grow faster than powers. Therefore, this equation is not bound as x approaches infinity. So in order to fix that problem, we can use 2 to the x instead of x squared at the denominator as well, and see if that helps. There, bingo. We have fixed the problem of limiting y values as x increases, and we have an S-shaped curve. It is limited between 0 and 1, and it does approach 1 when x approaches infinity, and it does approach 0 when x approaches minus infinity. And why is that? For some large numbers, say x equals 10, 2 to the x is a very large number, and 2 to the 10 divided by 1 plus 2 to the 10 is a number very, very close to 1. And as you can see, if x equals 0, the ratio equals 2 to the 0 divided by 1 plus 2 to the 0, which is 1 divided by 2, which equals half. And if you go further left, if you choose a very large negative number, as you can see, you will have a value very, very close to 0, but not exactly 0. So this has all the characteristics that we were looking for, and we should work a little bit more on this to generalize this format.